find the unique solution, or you could say particular solution, or you could say specific solution, to this second order differential equation. The second derivative of y is x e to the x. And we've got initial values, or initial conditions, making this an initial value problem. We want y at 2 to be equal to 3 and y prime at 1 to be equal to 8. So we've got some specific information about this unknown y, and we also know that it is meant to satisfy this very simple version of a differential equation, where really what this is saying is the second derivative of y is x e to the x. So if you want the original y, you just need to integrate this twice to cancel out the two differentiations. So let's crack on with that. So we got our, there we go, second derivative, x e to the x, and the initial conditions, what was it? Y at 2 was, I want to say 3, and y prime at 1 was 8, something like that. I will double check. Oh, look at that, I got it right. Yeah, sometimes I get it wrong. It's always good to go and double check before you launch into a lengthy calculation, as I say a lot. I say a lot, you know that. Okay, so if we want to undo this differentiation, just do it one at a time, integrating both sides. Okay, now we look at this, x e to the x. How can I integrate that? And substitution isn't going to cut it, but we might say, hey, I recognize we got sort of two well-known functions that form a product. We could try something like integration by parts. So here's what we're going to do. We're going to let our u be x, and our dv be e to the x dx. And so then our du is dx, and our v would just be e to the x. Okay. And then we can get, all right, u, v minus, and then v du. Well, I know how to integrate e to the x. So we get x e to the x minus e to the x plus c. Okay. And we could, I guess, group this a little bit. We could say x minus 1 e to the x plus c. So there's our derivative of this unknown function that we're trying to solve for. Now, we have an option. Okay? You don't always get this option depending on the initial conditions given in the question. But in this particular question, we have a value of y. So y at 2 is 3, but we also have a value of y prime. So if we wanted to, we could stop and solve for this c right here. We don't have to. We could keep going, get y by integrating this, and you'll have a plus cx and a plus d, and then use both conditions to figure out the c and the d. But while we're here at the first derivative, why not? Why not? Let's use this so we know y prime at 1 is 8. So if I plug in 1, I should get 8. So 8 should be y prime at 1, which will be 1 minus 1 e to the 1 plus c. Well, that's 0. So really we have 8 equals c. And so with our initial condition there, we can say, all right, the derivative, more confidently, is x minus 1 e to the x plus 8. Just solving for that concept. Again, we didn't have to, but I'm choosing to. So now I want to get back to y. We're trying to solve for that particular solution y. So we integrate again. So to go back from dy by dx, take an antiderivative or integrate. So we'll integrate on this side here. Okay. Now integrating 8 isn't going to be a problem. It's 8x, but what about x minus 1 e to the x? Well, that's going to require another integration by parts. We're going to let u be x minus 1 and dv be e to the x dx. So once again, our v is e to the x, and our u is just dx, because x minus 1 goes to 1. So we can, I'm going to need another sheet of paper here, but we'll have u v minus v du, and then of course the plus the 8x there, and then we'll have a new constant, a different c from before, but no harm in reusing the same letter. If you're particularly worried, call it c1, but I'm just going to call it c again, because we already solved for the first instance of c. Okay. And then integrating e to the x, yeah, we know how to do that. Okay. And oh, look at that, we can say x minus 2 e to the x plus 8x plus c. So this is what y should look like, but we don't know what this constant c is, and that's where we're going to use the other initial condition from our initial value problem, that we get 3 out from the y function if you plug in x equals 2. And so we get 3 is 0 plus 16 plus c. Doesn't take too long to realize c is negative 13. And so we finally have our particular solution, because we've just solved for that constant. So y, or you could say y of x, but I think I'm just going to stick with y, is x minus 2 e to the x plus 8x minus 13. There we go. That is the unique solution to our differential equation that also solves y at 2 is 3 and y prime at 1 is 8. All done.